In this video, we're going to talk about the idea behind if you have a gradient, how you can reconstruct the function that it came from. Just to kind of give an overview of the main strategy that we're going to use here. Since the gradient of the function is equal to the vector with all of its partial derivatives, organized, by component, we know that f has to be a combination of integrals of each of these. Or, more specifically, antiderivatives. So, like, for example, we know that f has to somehow look like the antiderivative of the partial derivative with respect to x. And we take that integral with respect to x. The partial derivative with respect to y integrated, or taking the antiderivative with respect to y. And then same idea for the partial derivative with respect to z. I mean, like, the main idea here is just that, okay, we took a derivative with respect to x, and now we want to undo it by taking the antiderivative with respect to x. We had the derivative with respect to y, and now we're undoing it, and derivative with respect to z, and now we're going to undo it. And one of the things about each of these, though, is that it kind of recovers at least slightly, or at least it can recover kind of slightly different information in each case. Because when we took the derivative with respect to x, for example, anything that was only in terms of y and z dropped off. So anything in terms of y will pop up when we take this integral here, and anything in terms of z will pop up when we take this integral here. So there's a lot of this kind of, we take all three of these pieces, and then we have to figure out how they fit back together. And a lot of this would probably become a lot more clear if we worked through some examples. So I have several here to look at today. Our first example, we have that the gradient of f is given by the vector 3i hat plus j hat minus 2k hat. And one of the first things that I'm going to do with this here is I'm actually just going to rewrite it like this. Okay, there we go. That looks a little bit more like what we've been working with. So we want to figure out where this came from. And the information that we have available to us is that this 3 was the partial derivative with respect to x. The 1 is the partial derivative with respect to y. And that -2 is the partial derivative with respect to z. So basically what we're going to do is we're going to go through each of these pieces and undo the derivative that had been done to it. So we know that f of x, y, z has to somehow be equal to the antiderivative of 3 with respect to x. So that's undoing the partial derivative with respect to x. And this is equal to 3x. But then, you know how when we take a derivative, or an integral, or no, a derivative, when we take a derivative, anything that's constant gets kind of chopped off, right? Well, same idea applies when we're taking a derivative with respect to x. Anything that's only in terms of y and z is also going to get lost. So we have to add back in this unknown function of y and z. I'm just going to denote it with a c, okay? And there may also be some constants that are kind of jumbled in there too. But the point is that anything that was only in terms of y and z had to have gotten lost in the derivative process with respect to x. So we just kind of want to make sure we account for that when we do this integral here. To kind of figure out what this missing piece might be, though, that's where the next two integrals come into play. So we have the integral of, now we're doing it with respect to y. We're going to look at that partial derivative with respect to y, trying to recover that piece of information. That's just going to be equal to 1. And then similarly, anything that didn't have a y in it, or mainly only had an x and only had a z, that had to have gotten lost as well. Okay, so I'm going to denote that unknown function with like a c tilde or something. Okay, and then we can do the same idea with the z component. So we're looking at the partial derivative with respect to z. That was -2. We want to undo that process. So that gives us -2z plus, and then again, same idea. We lost some function in terms of only x and y in this particular scenario. Okay, so now we have to figure out how all three of these pieces fit together to give us what f of x, y, z had to be. Well, we know that there has to be a 3x involved. And we know that we also want there to be a function in terms of y and z. And if we kind of look at these next two pieces here, when we took this integral, we know that we wanted to get a y back. And we took this integral here, we wanted to get a -2z, which means that we've accounted for this unknown function here in terms of y and z using what we recovered here and then what we recovered here, okay? Now, we want to make sure that we hit everything, that we took care of every single unknown piece here. So we want to make sure that we look at this right here. So we had some unknown function in terms of x and z along with this y. Well, the y has already been accounted for here. And this unknown function in terms of x and z, well, we had this 3x. That's already made an appearance, so that's taken care of. And we had this -2z. Which has also already made an appearance in our final equation. So that's taken care of as well. And finally, we double check this unknown function in terms of y, x and y. Well, 3x has already made an appearance and that y has already made an appearance. So that's really going to take care of that unknown function in terms of y and x. So we're able to kind of figure out what these missing pieces of information must be based on what was recovered by the other integrals. Now, one piece of information that is not recovered by any of these is just some generic constant, okay? We could still have some number that's been floating around like 2 or pi or e to the -3 times 4 or something weird. We don't really know what that is, and it got lopped off during any one of these derivatives, and it's not going to be recovered with any of these integrals. So I'm just going to say that that'll be plus some constant to take care of that piece of information. And one thing that's really nice about these problems, though, is that we're able to go back through and we can take the gradients to make sure that we got the right answer. So if we take the gradient of what we just recovered, well, partial with respect to x is just going to give me 3. Partial with respect to y is just going to give me 1. And partial with respect to z is just going to give me 2. So it does indeed check out. All right. So again, big idea here was we knew that each one of these components corresponded to a different partial derivative. We go through and undo each partial derivative and kind of check to see what kind of overlap and gaps that we're able to fill in based off of knowing that certain types of functions had to have gotten lopped off in the derivative process. Let's look at another example. In this one, we have that the gradient of the function that we start with, gradient of g of xy, is equal to x and then 3y squared. Okay, so this is our partial derivative with respect to x, partial derivative with respect to y. We're going to undo each one of these processes or each one of these derivatives and then see what kind of overlaps and what we can put back together. So we know that g of xy has to somehow be equal to the integral of x dx. So this is undoing the partial derivative with respect to x. Well, that's just equal to 1/2 x squared. And then when we took this derivative, anything that was only in terms of y would have gone away. So there's some unknown function in terms of y that we weren't able to recover with the integral, but that we know could still be there. So if we look at this piece here, taking this integral, we might be able to figure out what that missing information is. So we have the integral of 3y squared dy now instead of dx because we're wanting to undo the partial derivative with respect to y. Well, that's going to give me y cubed plus some unknown function in terms of x. Well, kind of putting this information together, well, I know that I have to have that 1/2 x squared and some unknown function of y. Well, when I look at my next integral tells me that there has to be a y cubed. So that unknown function in terms of y actually gets accounted for when I take that next integral, kind of fills in that piece of missing information. And we can say similarly, when we look at this integral here, we had this unknown function in terms of x, and the information about that got filled in right there. And both of them are taken care of when we put the pieces together. And then once again, we have possibly some constants that we weren't able to account for. So this would just be like plus some constant, like so. And as before, we're able to check. So if I take the gradient here, I'm just going to be left with x, because we'll have partial derivative of this guy with respect to x is just going to give me x, and then I have 3y squared. So it does indeed work out. Okay, I want to look at an example that's a little bit more involved in trying to figure out how to make the pieces fit together at the end. So here's an example of the gradients fxy equal to 3x squared y squared, and then 2x cubed y plus 2y. Okay. So this right here, partial with respect to x, partial with respect to y. All we got to do is integrate with respect to each one of those variables and kind of fill in the missing pieces with that. So we know that our original function can be recovered by undoing that partial derivative. So it's going to be integrating our partial derivative with respect to x, like so. And this is equal to, so I just integrate with respect to x, and I can treat the y as though it's a constant. It's just kind of along for the ride. So I only pay attention to the x here. I get x cubed y squared, and then plus some unknown function in terms of y. Okay, because again, maybe there was just something that had originally been here, like a plus, I don't know, y cubed or something. And when you take the derivative of just y cubed, it goes away. So we want to make sure that we're able to account for that. We also know that it's equal to the integral or the antiderivative of the partial derivative with respect to y. So undoing that derivative process with respect to y, it's going to look like this. And here we are going to get x cubed y squared, and then this piece, when we integrate that, is just going to be plus y squared. And then we still, it's possible to have some unknown function in terms of x. Okay, that maybe again kind of fell away when we took the derivative. All right, so now this time we kind of have a lot of different pieces that we want to put together, and there's actually some kind of overlap here. So in our previous examples, what we've been able to do is just kind of add all the pieces together, and that's what we get. But I want to be very, very clear that that is not always the case. Anytime there is some overlap like this, you want to make sure to only mention it once, because it's already been accounted for previously. So we start here, and we know that we need that x cubed y squared, and we know that we need some unknown function in terms of y. So now we're going to move down to our next line. And we look at this here, and it tells us that we have x cubed y squared plus some unknown function of x. Well, this x cubed y squared has already made an appearance. We actually don't need to account for it twice. It just needs to show up once. It's already been accounted for, so there's only one x cubed y squared here. But the y squared has not shown up yet, and our equation up here says we could still have some unknown function in terms of y, and y only, okay? So that's going to be the y squared. It's going to come from that right there. So the y squared here takes care of the unknown function in terms of y that we got there. Now, just to double check, to make absolutely certain we got everything, we look at this integral here and what we got back. We have an unknown function in terms of x, so we refer back to our equation in terms of x, and the only things that had x in them was that x cubed y squared. If anything else was going to have an x in it, it would have shown up here. So we know at this point that everything that's been taken care of, everything that has to do with this unknown function in terms of x, was already taken care of in this term here, which made an appearance right there. So having accounted for each one of these pieces, okay, so this only has to be accounted for once, and then the unknown functions, That's everything that we can get out of this information right here. And at this point, we just want to do the equivalent of doing the whole plus c thing. So we add a constant at the end. And once again, and actually I really highly encourage it when you're working with these that have a lot of different pieces to it like this, we can take the gradient to be able to check. So if we look at the gradient x, f, x, y, gradient or derivative with respect to x is just going to give me 3x squared y squared. And derivative with respect to y is going to give me 2x cubed y plus 2y. And this is exactly the same as what we started with, so we are good to go. Okay, that style of problem is a little bit more difficult, so I wanted to do one more example that looked like that. This time we're going to do something that has 3 components to it. So we have the gradient of f, x, y, z. Suppose that we start with that being x, y, z plus 2x, and then 1/2 x squared z, and then I guess my third component is going to have to go here on the next line, 1/2 x squared y plus z cubed, just like so. Okay. Well, we're going to apply the same idea here, where we know that this first component, that's your partial with respect to x, second component is partial with respect to y, and third component is now your partial with respect to z. And we're just going to go through all of the exact same steps. We're just going to have some extra pieces floating around. So f of x, y, z has to be equal to, first we take care of the x component here. So that's going to be integral xyz plus 2x dx. And after we integrate this with respect to x, treating the y and the z as though they're constants, we're going to get 1/2 x squared yz plus x squared, and then plus some function that is unknown in terms of y, and then this time we can also include the option of that function being in terms of z. Okay, so any function that's in terms of only y and z and no x's, that could have just fallen off when we take the derivative with respect to x, so we want to make sure that we account for that possibility. Next, we want to try to reconstruct from using our second component here. So that's going to be undoing the derivative in the y direction, so 1/2 x squared z dy, so antiderivative with respect to y undoes derivative with respect to y. So we have 1/2 x squared z, and then we get a y here because we're just treating this as though it's a number. And then once again, we could have the possibility of having an unknown function, this time in terms of x and z, like so. Finally, same process, but for the z component. So we're going to undo the partial derivative with respect to z. And this is going to be equal to 1/2 x squared yz plus 1/4 z to the fourth, and then plus some unknown function, I'll call it c hat or something, xy. Just like that. Okay. So now at this point, we're going to go down the line, figure out what overlaps, figure out what we need to do to fill in these missing pieces. So I know from my first part that we have to have 1/2 x squared yz and then plus x squared. Okay, just like so. So that takes care of this one. But we don't know what this unknown function in terms of y and z is. So we're going to turn to our next 2 pieces to try to fill in those missing gaps. So here we look at fxyz and recovered from the partial derivative with respect to y. And here the only information that we get out of this is that we have the 1/2 x squared zy, and we did not recover any new functions in terms of y. And so since this guy was already accounted for here, and we're not adding any new information about y, we can move on from this part here. So now we turn to our undoing the third component of the gradient here. And once again, we see this repeated information of 1/2 x squared yz. Well, that makes sense. We already have that. But some new information here is about the unknown function in terms of z that is mentioned both in the y case and in the x case, and that's going to be that plus 1/4 z to the 4th, like so. So let's go back through and check to make sure that we got all of our missing pieces. So unknown function in terms of y and z that wasn't already contained here. Well, y didn't really have anything new to offer, so that doesn't really contribute anything new. But z did offer this 1/4 z to the 4th. So that's that piece of information right there. If we look at unknown functions in terms of x and z here that don't have a y in them, okay, so not already accounted for here, we can look back up here what was recovered with x, and we gained an x squared out of that. That's already present here, so we're good to go there. And then we're looking for something that might be unknown in terms of z. Well, the only thing that came from z that we didn't already have here is that 1/4 z to the 4th, and that's already been recovered, so that's good to go. And then finally, we have the unknown function in terms of x and y. So going back up to what we know from x, we got x squared out of that deal. Again, already been accounted for. And then y did not contribute any information that wasn't already present in this equation. So no new information from that. So we've gone through, we've made sure that we've accounted for all the unknown parts, and everything that's in here is already here. So the only thing we have left to do is to add our constant. And that's pretty much it for that problem. So we've already gone through, we've computed this. We can go back through and check. So partial derivative with respect to x for my first component is going to give me x, y, z plus 2x. That checks out. Partial with respect to y, I'm going to get 1/2 x squared z. That matches. And then finally, for my third component, I'm going to have 1/2 x squared y plus z cubed. And then that constant, it just goes away in each part. And that does also match our third component that we got up there with our gradient. So I really, especially with problems like this where there's a lot of moving pieces to it, please, please, please make sure that you double check your work at the end. It's really nice to have that kind of built in and give you an opportunity to fix any mistakes that you might have made. But that's pretty much it to this video. Thank you so much for watching.